Okay, so let's get started. I'm going to go back to uh, gradient descent in a bit, and we'll consider how we might make it efficient. We saw before it was very inefficient. But first, one issue that will come up in our discussion will be solving systems like AX is equal to B, linear systems. And I want to talk about that a little bit first, okay? So a note on solvers, it's very important that you remember that if you've got a linear system like AX is equal to B, and you want to solve for X, it is a very poor thing, a very strongly deprecated thing, to calculate a matrix inverse of A or to do Gauss-Jordan elimination, okay? And the reason is that as the size, if A is n by n, then calculating the matrix inverse or doing Gauss-Jordan elimination will take like the order of n cubed operations. Okay, and so it gets very expensive very fast as you increase n. Okay, on the other hand, a lot of the matrices, if you want to think of the linear operators that we're using, if you want to think of them as matrices, they have a certain structure. Okay, and that structure can be used, and then you can use specialized solvers for solving. Okay. So in this case, I'm going to be using a tridiagonal solver later on. So let me discuss that first before we go back to steepest descent. Okay, so tridiagonal systems have matrices like this. You're trying to solve AX equals B. And A has a lower diagonal, in this case 3, 1, 3, which might have non-zero entries. It has a main diagonal, in this case 10, 10, 7, 4, and it has an upper diagonal 2, 4, 5. Now it's possible that on these three diagonals you have entries which are not zero. All the other entries off of these three diagonals are guaranteed to be zero in a tridiagonal system. Okay. Okay, so a linear equation that you might want to solve might look like this. Okay, so if you can tell Python, look, do a Gauss-Jordan elimination, do a calculate the inverse of this matrix. That will involve something like order of n cubed operations. Okay, but if you use the Thomas algorithm for this, for a tridiagonal system, then this will be of order n. Now, if you just look at this system, you don't have to go through all the steps for you don't have to go through all the steps of the Gauss-Jordan elimination because of all these zeros. So this is already very close to being in row reduced echelon form. So you just have to do one manipulation in the forward direction, and then you can do back substitution. Okay, so the Thomas algorithm looks like this. You've got a tridiagonal system. The lower diagonal, the entries are called AI. They're shorter, that's a shorter diagonal than the main diagonal system. That has entries B0, B1 up to Bn minus 1. And then there's an upper diagonal which has C0, C1 up to Cn minus 2. Multiplying some n-dimensional vector x is equal to some n-dimensional vector d. Okay, so what you should do as an exercise is you should confirm that if you do this to do a forward sweep, the steps that are shown, and then you do this to go backwards to do with a back substitution, then that solves for all the xi. And this is of order n rather than Gauss-Jordan elimination, which is of order n cubed. Okay, so I've given you the link to this discussion of the Thomas algorithm on Wikipedia. Okay. Whenever you are doing any numerical linear algebra, one of the things that you want to do is you need to consider when there is stability. Okay, you want to be able to, we discussed previously that you can get catastrophic round-off errors and so on and so forth. And so various measures are taken to ensure that that doesn't happen. So in addition to this algorithm, people might be doing other things to make sure that you don't have those types of problems. And people have also worked out that for particular algorithms, under what conditions are we guaranteed that we will have stability of the numerical algorithm? Okay, so it's important to look those up before you use one such algorithm. We have an entire course on numerical linear algebra, so I don't want to go through all of that, but let's say that we're okay with using the Thomas algorithm for tridiagonal systems, and we do it for the sake of having order of n operations rather than having order of n cubed operations, which is what you would get if you tried taking inverses or doing Gauss-Jordan elimination. Okay. So never write a line of code if you can steal it. Okay, so very helpful people have put up code for doing the Thomas algorithm. So I took one of those. I've given you the link for that. I made a few small changes because it was written for Python 2 rather than Python 3. Okay, so I don't know if I covered len before, but that comes up in this code. So len. So if I have a list with 3 entries and I ask for the len of that list, it returns 3. Okay, so you want to write an algorithm not for a 6x6 system, but for an n-by-n system. And so when you feed in the required arrays, it should be able to work out how big the system is. Okay, and you have a range. That's something like these sequences of values that we've discussed before. We've talked about list. We've talked about NumPy arrays. And we also have something which is called a range. So here in this case, my range is the range from 1 to 3. And if I ask you to print the things that are in my range, it will give you 1 and 2 and not 3. So starting from 1, going to 3, but not including 3. Okay. So that can be useful for loops, for example. Okay. There used to be something called xrange. If you're used to Python 2, there used to be something called xrange. That's no longer defined in Python 3. Okay, so here we have some, we have this code that I've taken from, I've given you the source that I've taken it from. And this uses the Thomas algorithm to do tridiagonal matrices. And basically what you have to do is, going back here, there's this lower diagonal which consists of elements AI. So you feed it AI as a list or as a NumPy array, right? It needs that. It also needs the main diagonal. So that can be a list or a NumPy array called B in this code. And then it needs the upper diagonal, which has entries C sub I And we'll call that a list, or that should be a list or a numpy array called C. And then it needs this right-hand side, which will be a list or a numpy array D. Okay, so this code should take in A, B, C, and D, and it should spit out X calculated using the Thomas algorithm. Okay, and from the original code, I've changed X range to range. That's for the forward sweep. Now you do the backward sweep, and you return the thing. Okay, I'll let you go through the nitty-gritty of the code yourself. Okay, so going back to our example, this is the example that we have before. So once again, I don't need to store this entire matrix, and there's no point for a large tridiagonal system. There's no point in storing lots of zeros, right? You just store the three diagonals, which have the non-zero elements, right? But if you were to, but I'm going to use this A, capital A matrix here on the left-hand side. I'm just going to use that to check my result later, okay? But this isn't required by the code. And if you find yourself writing code where you're storing a lot of zeros, then look for a specialized solver to do your problem. Okay, so that's what A looks like. Instead of this A, what we're going to give the algorithm are these three arrays. So the lower diagonal I'm calling A, so that's 3, 1, 3. The main diagonal is 10, 10, 7, 4, so that's called B. And the upper diagonal is 2, 4, 5, that's called C. You also need the right-hand side, 3, 4, 5, 6. And what you should do is you run this, feeding in all these arrays, and it runs the Thomas algorithm, and it pulls out a result. Okay, so that's what your x1, x0, x1, x2, and x3 should be. And well, did it actually work? Well, I'll take A times the result, and I'll subtract D, and that should give me 0. And okay, to a reasonable accuracy, I get the 0 vector. Not exactly, but very close. Okay. And what else might we do if I really don't want to write any of my own code? What might I do? Well, there's within the scipy.linalg, there's a submodule called sparse, and that has solvers for sparse systems, which are mostly zeros, if you think in terms of matrices. So it has solvers for sparse systems, including solvers for diagonally banded matrices like this. Okay. All right then. Is that okay so far? Any questions? Sorry, आप दोबारा क्या था?
सर लीनियर अलजेब्रा हम स्काइप में यूज अब ये कर रहा था, ये तो हम नंपी में नहीं करते लीनियर अलजेब्रा.
I think SciPy, you already have NumPy in it, right? But anyways, like I said, you can read through this and see that it has this. I think there's one called there's a solver. It's called Solve Diag or some name like this that you can use. Okay.
Okay.
All right. To go on to review what we did before. Okay, we had an analytic problem. Y prime is equal to y on the unit interval 0 to 1. This has infinitely many solutions, which would be y of 0 exponential times exponential of t. Numerical analog of the problem, we look for a vector u, and that's the entries u1, u2 up to un minus 1 stand for estimated values of the function at points along the unit interval. Okay, and this should be such that d0 of u minus d1 of u is equal to the 0 vector, where D1 is defined as, and D0 and D1 are defined as before. So D0 estimates is an average value of the estimates between nodes, and D1 is a simple estimate of the first derivative using the values, using the approximated values. Okay, the internodal spacing is delta, which is 1 over n minus 1. Okay, this is equivalent to looking for, if you define a functional f of u equals 1/2 LU inner product with LU, and you can make that equal to 0, then that means that LU is equal to 0. And then you've solved your problem. So this is an equivalent problem. And we said that this could be done using gradient descent. So you do this Taylor series. F of u plus h equals f of u plus the gradient of f of u inner product with h plus order of h squared. And if you run through the calculations, you will get that the gradient is the adjoint of L times u. So that's D0 adjoint minus D1 adjoint acting on D0 minus D1 acting on u. So once you've worked out the gradient, this is the way it works. Gradient points in the direction of steepest ascent. So minus gradient points in the direction of steepest descent. So given a u, find the gradient of f of u. Then u should be replaced by u minus lambda gradient, where lambda is some positive number. Keep repeating until your gradient is small or some other quantity of interest is made small. Okay, so one thing that we noticed was that the gradients were extremely sharp or spiky. So if I had 11 nodes, I start with u going from 1 to 2. That's my initial estimate. And then I say, okay, the first gradient that I calculate, what does its graph look like? It looks like this. Okay. If I have 101 nodes, the graph looks like this. It's extremely sharp. Okay. Okay. And if we had this discussion of the CFL condition, basically we got that lambda over delta squared has to be less than some maximum value. So if I decrease lambda by, so if I decrease delta by a factor of 2, so right, then what do I have to do? I have to do the similar thing for lambda, but this is squared, so lambda has to be reduced by a factor of 4, which means you'll take approximately 4 times as many steps to do the problem. Okay, so as the, if you're subject, if you have this problem of the CFL condition, as the internodal spacing goes to 0, that is, your delta becomes very small, the number of steps required will go to infinity. Okay, so steepest descent is very bad. Okay, except, well, there's a reason I taught it to you, right? There's a way around the CFL condition. Okay, so Sobolev gradients were developed by Neuberger in the course of developing a general theory of partial differential equations. And there's a basic idea. The idea is that you have an inner product space. The inner product it defines a norm, right? The norm of the vector squared is the inner product of the vector with itself. Okay. And so that defines a distance or a magnitude. And so the question is, with your norm or your distance, are you measuring the right things? Okay. And so what Neuberger would say here is that you're not measuring the right things with your inner product. Okay. D0 and D1 are quantities of interest in the problem, but you are not using an inner product which includes those. You are not using an inner product which involves d0 of u and d1 of u, even though these are quantities of interest in your problem. Okay, so there are, for any vector space, there are infinitely many possible inner product spaces, right? You have the vectors, and then you define an inner product on them. And we always default to the same inner product. But there are other inner products that you could use. In fact, there are infinitely many other inner products that you could use. So why not use inner products that will help you measure quantities of interest in your problem? Okay, so I'm going to define a new inner product. So I wrote the old inner product with angle brackets, the usual inner product. In Rn, I wrote with angle brackets. So I'm going to write this new inner product with round brackets, okay, to distinguish between the two. So I'm going to say that the inner product of two vectors u and v should be the inner product of du with d0v plus the inner product of d1u with d1v. And if you remember from your linear algebra how inner products work, you can bring this d0 here over this d0 over here. So this d0 over here can be brought over to the other side, provided you make it the adjoint. And when you're dealing with Rn, the adjoints are, and you think in terms of matrices, the adjoint is the transpose. So I'm writing that with a D, right? And similarly over here, I can bring this D1 over to the other side, and that's the inner product of D1 transpose D1U with V. And then I can combine the two of them. And so there's this distribution law for inner products, and I can combine them in this way. Okay, so previously we were doing steepest descent in a different inner product space. And now I want to do it in this new inner product space. Okay, so essentially, so the old inner product space we can call H02. That was Rn equipped with the usual Euclidean inner product. And we want to work in this new space, which we'll call H12. And that is the Rn equipped with this new inner product that I'm talking about. So what will happen? You've got a different inner product. A different inner product means you have a different norm, and you're going to calculate different gradients. So let's see if the gradients that we calculate here are any more useful than the gradients we did last time. Last time they weren't very useful because it's a very inefficient algorithm. Okay, well, okay, so once again, let's do the Taylor series. So when we did the Taylor series before, it was f of u plus h equals f of u plus the inner product of the gradient with h plus terms of order h squared. So in this new space, it's the same thing. It's f of u plus the inner product, the new inner product. Before I was using the nabla symbol, now I'm going to use nabla sub s for the Sobolev gradient in this different inner product space, right? Because it's in general, it's going to be different than the other one, okay? So the inner product of the Sobolev gradient with h plus terms of order h squared. So what does that mean? We compare term by term. And what that means is that this term here, d0 transpose d0 plus d1 transpose d1. This is the relationship. This gives us the relationship between these two inner products. Okay. So given the usual inner product, the Euclidean inner product, giving us a gradient, right? The relationship between the Sobolev gradient and the gradient we calculated last time is D0 transpose D0 plus D1 transpose D1 acting on the Sobolev gradient is equal to the Euclidean gradient. Okay, so right, remember remember what this is. This is inner product of D0 Sobolev gradient with D0H plus inner product D1 Sobolev gradient with inner product with D1H, right? So this is how we get this. Okay, so now you need to solve that equation. We know how to calculate the gradient, that is the Euclidean gradient. So we can calculate the Sobolev gradient from the Euclidean gradient using this equation. So steepest descent in this new space looks like, start from U, find the Euclidean gradient. Now solve that equation for the Sobolev gradient. Now, instead of U minus lambda Euclidean gradient, you should use U minus lambda Sobolev gradient and keep going until the Euclidean gradient is very small. Okay. Are there any questions so far? Okay. So, same code as before. This time we're going to do it with 4001 nodes. Okay. And I'm going to crank the step size up to 0.23. Okay. So what did we do before? Well, we have to have the time values, the t values. So that's lin space starting from 0, stopping at 1, n, in this case, 4001. Also, I want you to return the internodal spacing, which I'm calling delta. So that returns an array T and my internodal spacing delta. Okay, U, well, as before in the previous session, it starts from 1 and goes to 2 initially, and hopefully we're going to evolve that until we find a solution of our problem. Okay, initialize the space for the Euclidean gradient df of U. Okay, same calculations as we had before, same constants that appear in calculating the Euclidean gradient. Okay, so we saw two ways of doing it, right? We saw one was calculate the Euclidean gradient by hand. We saw the other one was, here's the functional. Use auto differentiation to extract the gradient. Okay, so now I've got this equation to solve. D0 transpose D0 plus D1 transpose D1 acting on the Sobolev gradient is the Euclidean gradient. Okay. And it turns out that that's a tridiagonal system. So I'm not going to do some sort of invert a matrix or do Gauss-Jordan elimination. I don't need to. Instead, I'm going to use this tridiagonal solver. Okay, so I enter, so A equals NP full, n minus 1. So the lower diagonal has n minus 1 elements. And the entries look like minus 1 over delta squared plus 0.25. Okay. The main diagonal, the entries, there are n entries down the main diagonal, except for the first one and the last one, they look like 2 over delta squared plus 0.5. Okay, the first one is 0.5 times what this gave me. And the last one is a half of what this formula gave me. Okay, and then I have these values. C is the upper diagonal, and there's n minus 1 entries of the upper diagonal, and each of these entries is minus 1 over delta squared plus 0.25. Okay. Any questions so far? Okay, so that's how you can create NumPy arrays where all the elements are the same. Okay, using np numpy.full. Okay, so now we begin our evolution. This is again as we did before. We're going to evolve while the norm of the gradient is bigger than some number. Okay, I calculate as before. Here I'm calculating the Euclidean gradient. I'm checking its magnitude. And now the extra step this time is that I use the Thomas algorithm solver to calculate using the upper diagonal, lower diagonal, main diagonal, and upper diagonal. And the right-hand side is the Euclidean gradient. Using the Thomas solver, I can extract the Sobolev gradient. And now instead of taking a step in the direction of the Euclidean gradient, I take a step in the direction of the Sobolev gradient. We'll count the number of steps that are taken, and we will then plot against a solution, some constant times exponential of t. Okay, what happens? Okay, so once again, let's see. Okay, this time it takes only 120 steps. So that's with 4,001 nodes. Takes only 120 steps, and it gives me something very, very close to the two curves are basically on top of each other. Okay, so let's do a comparison. Remember, for 11 nodes, the initial gradient was very spiky for the Euclidean gradient. But the Sobolev gradient looks like this for 11 nodes. It's very smooth. Okay. For 1,001 nodes, it's very smooth, and it looks like essentially the same curve, right? And if I do the experiments, okay, I can use the same step size with the Euclidean gradient. As I increase the number of nodes, which means decreasing delta, I also had to decrease the step size lambda. But here I can use the exact same step size as I go from 11 to 21 to 41 to 81 to 4,001 nodes. I can keep the same step size. That means I'm not subject to the tyranny of the CFL condition. And the number of steps, well, okay, with 11 nodes, it was 86 steps, and with 4,001 nodes, it's still only 120 steps to get to a solution that looks very much like what we would expect. Okay. So what's the cost? The cost here is finding the Sobolev gradient. So there's an order n. If I'm using a Thomas algorithm, there's an order n cost at each step. But I have to do very few steps in comparison to doing this with the Euclidean gradient. Okay, this is almost the same number of steps, right? Whereas no matter how fine you make your internodal spacing. Whereas with the Euclidean gradient, the number of steps would be going to infinity. Okay. So there's an order of n extra costs at each minimization step, which is your, if you use the Thomas algorithm. Okay. Now, we could also use a conjugate gradient solver if we wanted. That would be more expensive at first. It would be less as we go along. So the cost would go down compared to what we've done. Okay. Are there any questions at this point? Okay. We move on to the initial value problem. So what if you've got something like this? You have the same differential equation that you had before. Y prime is equal to y. And now we will say that, sorry, that shouldn't be a y prime. That should be y of 0. So there's an initial value that y has the value 1 at 0. So the solution, now there's only one possible solution, and that's the exponential function from 0 to 1. Okay, so the numerical formulation is as before, a minimize f of u, the same f of u that we had before, except now it's subject to the condition that the first entry of u should be equal to 1. Okay, and that creates a little bit of a difference than compared to what we did before. Okay, so one thing is that you're going to start by estimating. If you know that the initial value should be 1, then your initial guess should have initial entry 1. Okay, and as the system evolves, as you're reducing the squared error, you should want to stay in that. All of your estimates should have initial entry 1. Okay, and what that means is, what does that say for the gradient? What property do you want for the gradient so that moving in the direction of the gradient doesn't change the initial entry of your estimate u? Well, if you insist that your Euclidean gradient vector should have initial entry 0, then that means that when you take u minus lambda gradient, if you think of what's happening to the first entry of that vector, that won't change. Okay, so you want your gradients to live in this space, the subspace, in which all the initial entries are 0. So all the gradients that you're going to calculate, these Euclidean gradients that you're going to calculate, they should all have initial entry 0. Okay, and so we're going to need a projection that will take you from the gradient that you have to the gradient that you want. You're going to calculate some gradient which maybe does not have initial entry 0, and you want to project it onto the subspace which has an issue in which all the vectors have initial value 0, right? So you did projections in your linear algebra course. Okay, so one way of doing that is to say, I've got a vector v0, v1 up to vn minus 1. I want to find the nearest vector w, which has entries w0, w1 up to wn minus 1, such that the first entry w0 is equal to 0. And I want to find the closest such vector. Okay, that's what projections do. They project you from a space onto a subspace and the closest point in that subspace. Okay, so if you look at the distance between those two vectors, or the 1/2 the distance squared between them, that would look like v0 minus w0, but w0 is supposed to be 0. So v0 minus 0 squared plus v1 minus w1 squared up to vn so n minus 1 minus w sub n minus 1 squared. I just take a half out here. It doesn't really matter, but it just makes the arithmetic easier. Okay. Okay, so what you do now is you differentiate with respect to the wi, and the optimal solution, the minimum of this, will occur when when the derivative of I with respect to each of the wi's is going to be equal to 0. And you should confirm that this will happen with W0 is equal to 0 and Wi is equal to Vi otherwise. So basically all you need to do is calculate your Euclidean gradient as you had before, and then use the projection and projection pi. And pi, what pi does is it acts on a vector in this way. It leaves everything else alone, but it turns the first entry into 0. Okay. All right. So now, if I take a look at my code using steepest descent in the Euclidean space, the only difference is that instead of calculating, I just set that first entry of the Euclidean gradient equal to 0. Okay, so that gives me, otherwise everything else is the same as we had before. And well, we run along, and remember, once again, this is the Euclidean space. So steepest descent is very inefficient. And the last entry should be what? It should be the exponential function at t equals 1. So it's this Euler's constant E and 2.7188. Okay, it's not too bad. An estimate for E. Okay. Okay, so is that all right? Is it understood why we're setting that first entry to 0?
Yes, sir. Kind of makes sense.
Okay. All right. So now, what are we going to do? We need to. We will go through all the same reasoning that we had before. From the Euclidean gradient, which is pi times, well, but this projected Euclidean gradient, we want to get the Sobolev gradient. So the idea is it's the Sobolev gradient that you would have had before, except you remember you had this equation before, but without the pi, without the pi's in them. Now, if you stuck a pi, projected this with pi on the right-hand side, you have to project this with pi on the left-hand side. So now you have to solve this. Okay. So that would give you a new, a slightly different Sobolev gradient with, again, we can use the Thomas algorithm to do this if we want. And once again, very efficiently, 81 steps, gives you a very good answer. Okay. All right. So a note on the solver. The way to guarantee that the tridiagonal solver will always give you 0 in the first element would be to have the first row is all zeros, except the first entry is 1. And the vector that you're acting on, has a 0 on the first, has a 0. So 1 times what gives you 0? Well, 0, right? So you would take your D0 transpose D0 plus D1 transpose D1. That's the matrix you were working with, if you want to think in terms of matrices. And you, what pi basically does is it takes that first, the first row, and says, well, it's all zeros except for the entry in the corner, which is 1. Okay, that will do it for you. Okay. And if you want to use a conjugate gradient solver, the way you would do it, in a conjugate gradient, you keep using this operator, D0 transpose D0 plus D1 transpose D1. Whenever it acts on a vector, what you should do is you should say, well, okay, so whatever vector I'm getting as a result, its first entry its first entry should be 0, and that will work for you. Okay. All right, so are there any questions? You sure? Okay. If there are no questions, then I will see you on Friday. I'll have a bit more information about the midterm at that point. Okay. I'll see you on Friday.
Thank you, Professor.
Yeah.